Hello, Calculus 1 students. I'm going to introduce calculus to you in this video. Also going to go over our first section that we have to do, which is we're going to begin in chapter 2, so section 2.1. So just to introduce calculus to you, the word calculus is a Latin word that actually means little pebble. So what in the world is that about? So, back in the ancient days, they would use little pebbles to help them calculate. And they came up with something called an abacus, which is putting these little pebbles, somehow putting them on a wire so that you can slide them. And that's where we get this abacus from. So calculus is kind of an ancient word that just was kind of a synonymous word with doing math. So ancient people were very concerned about doing practical things like calculating the area of a field, or the volume of a pyramid or something like that. So, and they got really good at figuring out quick ways, like formulas for calculating the areas of rectangular or triangular or any polygonal shaped field. But what they struggled with, and this has been a struggle for millennia in the course of human history, how to deal with not just straight edges and straight lines, but curves. Like, what if you had a field that was adjacent to a river? Like, what's the area of that guy? And, they came up with some interesting, smart ways to do that. They said, well, let's just make that into a polygon. We can calculate the area of the polygon, and it'll be a little too small in this part, but it'll be a little too big in this part. And so that'll kind of account for each other, and we can get really close to it. But they were still concerned about, could we do this a better way? Is there a way we can get closer and closer to the actual area of a curved surface? And that brings it, let's fast forward a little bit to the 16th and 17th centuries. In the 16th century, you had this guy named Rene Descartes. He was a mathematician and a philosopher and a theologian, and he was a general bad dude, and I mean bad as in good. And he came up with kind of a way to visualize how two quantities are related to each other if you put the two quantities on these perpendicular axes. Let's let this be an x quantity and a y quantity, and let's put how these things are related to each other, and make graphs out of that and visualize it. So that was in the 16th or in the end of the 16th, beginning of the 17th century, somewhere in there. And about 50 years later, after he introduced that concept, these two guys, independently of one another, in two separate countries, came up with calculus. One of them's name was Isaac Newton. The other one's name was Gottfried. I don't even know if I'm spelling this right. You probably won't have heard of this guy, Leibniz. But Leibniz was a bad dude too, and so was Newton. And there was kind of a big controversy about which one of them came up with it, truly invented it. But today we benefit from both of these guys' work, and they use different notation to do their work, and we kind of have a mixture of their two notations even today. But I thought it was very interesting that out of the thousands and thousands of years of thinking about these problems, these two guys kind of got it at the same time, and completely independently of one another. It's almost like God just kind of said, "Here you go. Here's calculus. Go. Here. Kind of just let that disseminate to the human race." And these two guys got it at the same time. So, and when it was back then, they didn't call it calculus, they called it the calculus. And what it was aiming at was the ability to calculate the incalculable things, like the area of a curved surface, the slope, the instantaneous rate of change of a curve rather than just a line. Those kinds of questions. one classic example would be something like if, let's say, here's a wall, and I am walking toward that wall. So to get to that wall, I'm first going to have to get halfway to the wall. Then I'm going to have to get halfway again, and then halfway again, and then halfway again, and halfway again, and halfway again. And I can't even draw it that close anymore. So, and that's got to go, like, how far could you take that? You could take that infinitely far. And you could say that means you have to do an infinite number of things, which means you would actually never get there. And that was a paradox that was kind of introduced in the ancient world by a guy named Zeno. He liked to introduce these mathematical paradoxes, and he said you'd never get there. Another way he introduced it was, I believe it was almost like a tortoise and a hare kind of a fable, where he said give the tortoise a head start, and for the hare to catch up with him. Or maybe he said it with Achilles, the really fast guy, or whatever his name was. Could he catch the turtle? Well, in order to catch the turtle, he would first have to get to where the turtle was when he started. But by the time he did that, the turtle would be a little further. Then he would have to catch where that turtle is then. But by the time he did that, the turtle would be a little further. And then he would, and you could continue on with that little series of thoughts infinitely. Again, a paradox. And this is kind of just the paradox of what infinity does to us anyway, because of our finite minds. Again, Deuteronomy 29:29. The secret things belong to the Lord, the things that require an infinite mind. But the things that are revealed belong to us and to our children, so that we may obey all the words of this law. So that's the things like calculating the area of a rectangle. We can do those kinds of things. But as far as being able to know the ratio of a circle's circumference to its diameter, we will never know. We can get close, 3.14159, blah, blah, blah. But the exact thing is impossible for us to fit it into our finite minds. But calculus is interested in allowing us to get closer and closer to dealing with these transcendent, infinite mathematical things. Introducing session 2.1, Newton, the story goes, is he sitting under a tree, he sees an apple fall to the earth. And he starts, he has this hypothesis, maybe there's some sort of an attractional force causing that to happen. But then he looks up and he sees the moon, and he says, well, but why isn't the moon just kind of like a big apple? Like, why doesn't it fall to the earth the way this apple does? And he kind of got this idea that maybe it has to do with the distance that the object is from the earth. And he did some more thinking on that, and he came up with a hypothesis and tested it. It came out to be a very accurate hypothesis, and that was that the gravitational force is inversely proportional. This means proportional. So it's inversely proportional to the square of the distance that the objects are apart. And so it turns out to be a function that looks kind of like that, where this is the distance that the two objects are apart, and this is the force of gravity between them. And so as you get further and further, the force gets smaller and smaller. But he wanted to figure out, well, how can I figure out the rate of change of that thing? It's not a line. Like if you're this far away, how much is that changing as you get a little further away? If it was a line, it's easy to calculate the rate of change, because you just take 2 points on that line, and the rate of change of the vertical variable with respect to the rate of change of the horizontal variable gives us the rate of change, which we call the slope. It's delta y over delta x, or the rise over the run, or the change in y over the change in x, or y2 minus y1 over x2 minus x1. All those are the ways we think about slope. And the cool thing about a line is it doesn't matter what points you pick. You're always going to get a proportion, a ratio that is equivalent to any other 2 points that you pick. So because these are similar triangles, so you're going to get the same slope no matter where which points you choose. But on this curve, if this was a curve, right, if you pick this point and this point, you would get a steeper thing than if you pick this point and this point. So you won't get the same ratio for a curve everywhere. And so Newton, that was kind of a dilemma for Newton. So Newton, what he did was he said, I'm going to take 2 points. All right. And this can be any function. He said, I want to generalize this. I don't want it to be just a specific problem. I want it to work for any problem. So let me call this any function. Let's call this function f of x. It's some function of x, right? So the y coordinate will be calculable according to some function with x. So if I call this x, and then this is the point x, f of x. Okay, so the y coordinate of that point we can call the y coordinate f of x, because it will be calculated according to some function with an x in it. And then I'm going to I'm going to go to another point, and I'm going to say that the amount that it takes for me to slide over to get to this other point, I'm going to call that h. Why h? I'm not real sure, but it's just h. That's the convention. So then this x coordinate, instead of saying x2, I'm just going to relate it to x. I'm going to say it's x plus h. Okay, and so then this y coordinate of this second point will then be f of x plus h. So this point has the ordered pair x plus h, f of x plus h. So we have these 2 points, and I can calculate the slope of what might be called we call it a secant line. The slope of the secant line. The secant line, a secant hits a curve in more than one place. All right, if you think about it as a circle, a secant passes through the circle in 2 places. And you can kind of let the secant get closer and closer and closer to the edge of the circle until that secant actually becomes a tangent to the circle. Tangent, so secant crosses curve, C-U-R-V-E, at 2 points, whereas a tangent only touches the curve at 1 point. Where do we get the word tangent? Think of another word that's like tange something. What's another word that we use? Tangible. What does tangible mean? It means you can touch it, and that's where the word tangent is related to that. It means that it touches the curve, just touches it. So Newton really he thought about the secant line in order to get to his goal of not the secant line, but the tangent line. He really wanted this secant line to kind of get closer and closer and closer and closer to becoming a tangent line, a line that just touches that curve in one place. And he figured that if he could find the slope of the line that is tangent to the curve at that point, then he could find the instantaneous rate of change of that curve at that point. And this is how he continued to work on it. He said, the rate of change of the secant line would be, y2 minus y1 over x2 minus x1. But using this notation, it would be f of x plus h, that's the y2, minus f of x, that's the y1, over x plus h, that's the x2, minus x, that's the x1. And there's even a simplification that we can make from here on the bottom. The x and the minus x can actually cancel, so that we're left with just h. This is a very important concept. This calculates the slope of the secant line, which calculates the rate of change, the average rate of change between 2 points. But now Newton said, let me introduce another word. Let's put some more language to this. So let's take a limit as h approaches 0. Let's figure out, in other words, like we can't calculate it when h is 0 because then we're dividing by 0, but maybe we can calculate it as h gets closer and closer to 0. Think about this problem right here, x squared minus, let's say x squared minus 9 over x minus 3. Let's just think about this function. What comes to mind when you think about what is interesting or what characteristics this function has? You might think from your pre-calculus days, well, something weird is going to happen to this function when x is 3 because you're going to be dividing by 0. You might also think to yourself, we could also maybe simplify this function if we factor the top as a difference of squares, that then could cancel the x minus 3 on the bottom and give us this new function, which is just x plus 3. So this function and this function, are they the same function? They almost are, but there is one difference. These two functions give me the exact same answers, except at one place. At 3, this function is defined, but this function is undefined. So at 3, this function would give me just 6, but this function would give me an undefined, absurd, unable to compute kind of answer. I want to show you this in a calculator if possible. All right, this is something we were able to do in class, but I can't do it. I can't bring up a calculator that would do this on the computer. But if you'll graph this in your TI-84, graph this function, go to zoom integer, then you will be able to see the whole. You should see something like this. You should see something like that, where it actually has a blank spot. When you hit zoom integer, it'll have a blank spot there at 3. And then if you trace it, you'll be at 2. X will be 2, and y will be 5, and then x will be 3, and y will be, and it'll have no answer. And then it'll say x equals 4, and y will be 7. Then I want you to zoom in, hit zoom in, and zoom in on that hole. And then you could do something like, then it would give you something like x equals 2.75, and y equals 5.75. It's still going to say x equals 3, y equals a blank spot. You could do x equals 3.25, and y will equal 6.25. And you can zoom in again, and it'll get closer and closer and closer, like to where maybe x equals 2.999999, and y will equal 5.999999, or x might equal 3.000000001, and y would equal 6.0000001. And you can continue to do that for a long time. The point being, you can't say what this function equals when x is 3 because it's undefined there. But you can say what the function approaches as x approaches 3. You can say that as x approaches 3, the limit as x approaches 3 of this function is equal to 6. That's the language and the concept that Newton emphasized when he did this limit. He said, I might not be able to do it when h is 0, but I can do the limit as h approaches 0. Leibniz, for his part, he used this notation right here. He said dy over dx, right? So delta y over delta x, that's just a slope. But dy is like an infinitesimal change in y over an infinitesimal change in x. So, which is exactly what this is doing. This is the change in y as h approaches 0 is an infinitesimally small change, and as h approaches 0, that's an infinitesimally small change in x. So Leibniz had that notation to signify that. All right, so this right here, this right here is the kind of the apex of where we're going in calculus in the first half of it. In fact, this has a name. I'll go ahead and give away that thunder. The name of this is the limit definition of the derivative. You're gonna hear that word over and over again this quarter. I'm not really teaching this yet. What I'm doing is introducing it. I'm saying this is where we're going, so that everything we're about to do, you'll kind of have an idea of we're doing this in order to get to here, in order to get to a better understanding, a foundation for this idea of a derivative. Derivative, it gives us an ability to find the rate of change of any mathematical function. We can find how that function is changing, of the rate of change of the dependent variable with respect to the independent variable. As far as physics is concerned, a lot of times that has to do with the rate of change of position with respect to time, which gives us velocity, or the rate of change of velocity with respect to time, which gives us acceleration. And so we're able to, if we have a distance or a position function, we can find the velocity. If we are given a velocity function, we can find the acceleration, which is really important concepts in physics. All right, so let's move on now to section 2.1 in the textbook. Somebody put a lot of thought into this textbook, so I'm going to give it its due. We're going to read how the textbook communicates these concepts. So an overview of this. Mathematicians of the 17th century were keenly interested in the study of motion for objects on or near the Earth and the motion of planets and stars. This study involved both the speed of the object and its direction of motion at any instant, and they knew the direction at a given instant was along the line tangent to the path of motion. The concept of a limit is fundamental to finding the velocity of a moving object and the tangent to a curve. In this chapter, we develop the limit, first intuitively and then formally. We use limits to describe the way a function varies. Some functions vary continuously. Small changes in x produce only small changes in f of x. Other functions can have values that jump erratically, or they increase or decrease without bound. Let me explain that a little bit. The notion of the limit gives a precise way to distinguish between these behaviors. So for example, if you have 5 people in a room and then another person walks in, that value jumps from 5 to 6. It skips over an infinite number of numbers between 5 and 6. That would be a discrete function, not a continuous function. So it would not be that a small change in time produced a small change in the number of people. In that case, a small change in time produced a jump in the number of people. But if you take, say, something like, let's say, the average weight of the people in the room, that could vary continuously. It could be, it could be 130 pounds, or it could be 131 pounds, or it could be anything between 130 and 131. It could be any of those infinite possibilities between 130 and 131. So that would be an example of a continuous function, that a infinitesimally small change can occur without it having to be a jump from one number to another. All right, 2.1, rates of change and tangents to curves. Calculus is a tool that helps us understand how a change in one quantity is related to a change in another. How does the speed of a falling object change as a function of time? How does the level of water in a barrel change as a function of the amount of liquid poured into it? We see change occurring in nearly everything we observe in the world and universe, and powerful modern instruments help us see more and more. In this section, we introduce the idea of average and instantaneous rates of change. Okay, so that's the big idea in this little section. Average rates of change contra instantaneous rates of change. We're going to distinguish between those in this section and show that they are closely related to the slope of a curve at a point P on the curve. We give precise developments of these important concepts in the next chapter, but for now we use an informal approach so that you will see how they lead naturally to the main idea of the chapter, which is the limit. The idea of the limit plays a foundational role throughout calculus. Average and instantaneous speed. In the late 16th century, Galileo discovered that a solid object dropped from rest near the surface of the earth and allowed to fall freely will fall a distance proportional to the square of the time it has been falling. This is free fall. All right, so this is what Galileo discovered mathematically. If you're measuring in feet, then the distance an object falls, y, will equal 16 times t squared. All right, if you take physics, you can learn how he actually figured this out and how you can derive this. But for now, you just have to accept this, that the distance an object falls is equal to 16t squared. If we're talking about feet. If we're talking about meters, it would be, the distance would equal 4.9t squared. All right. That actually has to do with the fact that the acceleration due to gravity in feet is 32 feet per second squared, and half of 32 is 16. And in meters, the acceleration due to gravity is 9.8 meters per second squared, and half of 9.8 is 4.9. Again, take physics to learn more about that. A moving object's average speed during an interval of time is found by dividing the distance covered by the time elapsed. And you already know that. Speed is distance divided by time. Speed is distance over time. The unit of measure is length per unit time, kilometers per hour, feet per second, or whatever is appropriate to the problem. Example 1. A rock breaks loose from the top of a cliff. What is its average speed during the first 2 seconds of falling? Or, part B, during the 1 second interval between the first second and the second second. All right, let's take a look at that. So what we've got here is we've got this function, 16t squared, is a parabola. And so if this is time, this is the distance that the object has fallen, this would be the distance that it has fallen in 0 seconds. So it hasn't fallen any distance. And then in 1 second. And then in 2 seconds. So question 1 is asking us, question A that is, what is the average speed during the first 2 seconds of falling? So in other words, between when it started and after 2 seconds, what is the speed here? And remember, speed is distance over time. So that means that if we get, or we could also say it's the change in distance over the change in time, which is kind of saying the same thing. So between these 2 points, the change in distance would be kind of like finding the rise between these 2 points. The rise, this is the change in distance. And the change in time is kind of like finding the run of that, the change in time. So what are we dealing with then? The speed is the slope of the distance graph. Speed is the slope of the distance function. All right, because it's distance over time. The change in the distance is the rise. The change in the time is the run. And this is slope. This equals slope, which equals, we could say, y2 minus y1 over x2 minus x1. All right, we could also say, we could use a different notation for this. We could say that's the same thing as f of x2 minus f of x1 over x2 minus x1. All right, so using that, we're going to use Galileo's equation, y equals 16t squared, or we could say f of x equals 16t squared, either way. And so let's find these 2 points using that. So f of 0 would be 16 times 0 squared, which is just going to be 0. And f of 2 would be 16 times 2 squared, which would be 16 times 4, which is 64. So these are my 2 points. My 2 ordered pairs for these 2 points would be 0, 0, and 2, 64. And now I'm just finding the slope between the 2 points. So the answer, part A, is just going to be 64 minus 0 over 2 minus 0. y2 minus y1 over x2 minus x1, which is 64 over 2, which is 32. That's the answer to part A. That is the average speed, during the first 2 seconds of falling. All right, I want to take a closer look at that, okay? The average speed is the slope of this, what we would call a secant line. The secant line. The secant line is a line that passes through 2 points on the curve. Find the slope of that secant line, and you found the average rate of change. Average rate of change. So if we're talking about, if this is a distance function, the average rate of change might be the average speed. It doesn't always have to be speed, but for that example, we're talking about speed. All right. Now, during the first few moments of falling, you can kind of see that the speed is not, it's less than the average. During the last moments of falling, the slope of this is more than the average. And at some point in this thing, the slope of this thing is exactly the average. But at some moments it was going a little slower, at some moments it was going faster, but the overall average will be the slope of this secant line. All right, part B. Now, instead of finding the average speed over the first 2 seconds. In other words, between time 0 and time 2, I'm now finding the average speed between the first second and the second second. So between time 1 and time 2. So I am finding now the speed between this point and this point. So now instead of finding that blue line, the slope of that blue line, I'm now going to be finding the slope of this red line. So you can see that the average speed we're going to get here is going to be greater than the average speed that we found earlier, because it's going to, on average, go faster during that last second of falling than it did during the first second of falling, because it's getting faster the whole time. All right, so all I have to do is find an ordered pair for this point and find an ordered pair for this point. So let's do that. So we're going to find f of 1, and f of 1 would be 16 times 1 squared, which is going to be 16. And we already found, so that's the point 116. That's the ordered pair for that point right there. And we already found f of 2, that was 64. So the point 264 is the ordered pair for this point right here. So to find the slope, to find the average rate of change, we find the slope of that line. y2 minus y1, 64 minus 16 over x2 minus x1, 2 minus 1. That gives us 48 over 1, which is 48. Notice it makes sense that we got that answer, that we got 32 for part A and we got 48 for part B, and that makes sense. Over the whole 2 seconds, it had a less of an average rate of change, less of an average speed than it did over the second half of that 2 seconds, in which case it was going a little faster than it was during the first half. Okay, you can see right here, they do the same thing that we did. They got the same answers we got. And now they say this: we want a way to determine the speed of a falling object at a single instant. And this notation right here, you could say t0 or t sub 0, or you could even say t0. Instead of using its average speed over an interval of time. To do this, we examine what happens when we calculate the average speed over shorter and shorter time intervals starting at t0. The next example illustrates this process. Our discussion is informal here, but it will be made precise in Chapter 3. So example 2. Find the speed of the falling rock in example 1, not the average speed between the 2 times, but the instantaneous speed at those 2 precise moments. So I want to find the instantaneous rate of change, the instantaneous speed at the moment that 1 second is on the clock. And then again at the moment that 2 seconds has hit the clock. All right, look, watch this. We can calculate the average speed of the rock over this time interval. This is what I showed you before. From this moment time to some other moment of time that is just a little bit more than that first moment. Okay, and then we end up with this function f of x plus h minus f of x over h, which is what we saw before. Now let's use the notation that they used here. Instead of x, they're using t. So we could say f of t plus h minus f of t over h. And that's what they're doing here. F of t, or if you want to say f of x, well, it really doesn't matter, but it equals 16 t squared. So f of t plus h would mean that we're going to substitute t plus h in the place of t. Right? F of t plus h means I'm substituting t plus h in the place of t. So let me do that. 16 times t plus h squared. Okay. And so when you do that, you end up with, if you plug it into here, using this, f of t plus h, that would be 16 times t plus h squared, because that is f of t plus h, minus f of t. F of t is this, so minus 16t squared over h. So looking at how they have this written, they say this: we cannot use this formula to calculate the instantaneous speed at the exact moment of t naught by simply substituting h equals 0, because we cannot divide by 0. That's the problem. You can't do it with a curve. And the reason you can't do it with a curve is because you can't divide by 0. You can't truly make it be at one instant on a curve, because then you'd be dividing by 0. Right? That's going to be the magic of calculus. That's going to make it happen. But we can use it to calculate average speeds over increasingly short time intervals. All right, so watch this. Let's try to understand what we're looking at in this table. All right, this gives you the average speed when the moment you're looking at is 1, and the next moment you're looking at is this far away from 1. So the average speed when we're looking at the moment of 1, and then we go 1 second away from 1, which is 2, is 48. That's what we found in the example earlier. But let's decrease that amount of time after 1 second. Instead of going 1 whole second later, let's just go 1/10 of a second later. So when you go 1/10 of a second later and you use this formula, that means you're just plugging in 0.1 for h. You're going to do this calculation and you're going to get 33.6. Well, let's get even more precise. Let's go a 100th of a second beyond 1. So that would be, let me draw this for you. So what we're doing here is okay, here's 1. Here's 1 away from 1. But then they get closer. Let's get only 1/10 away from 1. So instead of finding this secant line, let's find this secant line. Then let's get even closer. Let's get 100th away from 1, and that would be this secant line. Let's get even closer. Let's get 100th away, 1,000th away, 10,000th away. So now it's like we have to zoom in on this thing. Now we're looking at something like these 2 points, where this is now only 1/10,000th of a unit apart. And how close could we get? We could get way closer. We could get 1,000,000th of a unit away, 1,000,000,000th of a unit away, 1/quadrillionth of a unit away. And then even infinitely closer than that. How close can we get? As close as you can imagine. Right? That means this h is getting infinitely close to 0. We're bringing these 2 points infinitely close together. So is h 0? That's kind of a magical question. I'm not going to answer it because I don't know if I can. If h gets infinitely close to 0, is that the same thing as it being 0? That's just the magic of calculus that is kind of incomprehensible. It really truly is about it's just going to be kind of incomprehensible and almost magical. We're going to be able to do with calculus the calculus what, according to our understanding before it, can't be done. And that's what the language of a limit is. It's saying we're going to get infinitely close. Are we going to be that thing that we can't be? Well, maybe. So, anyway, you can tell what this limit is going to. As we get as we get closer and closer together with the secant line toward the tangent line, where these points are becoming like the same point, they're getting so close together. So we're finding the slope of the tangent line at this instantaneous speed, in other words. What is this value getting closer and closer to? Well, hopefully you can tell basically that this is going closer and closer to the value 32. All right. Then they do the same thing here. If we want to know the instantaneous speed at 2, so here, like what is this? What is the slope of that tangent line? Well, if h is 1, it's 80. That's not a very good estimate. Let's get closer. Let's make h be 0.1, 65.6. Let's make it be 0.001. Again, we're making these points get infinitely close together. And what is this value going to? It appears that it's going to go as we draw the points closer and closer together to become one point at the moment that t equals 2. The value of this rate of change appears to be going to 64. So that's just that. Again, this is not a precise way to define the limit that we're talking about. This is trying to build your visualization of what's happening. It's trying to build your intuition, your feelings about what is going on here, so that you can connect with what this is going to accomplish when we get to the precise definition of the limit. All right, the average speed on intervals starting at t0 equals 1 seems to approach a limiting value of 32 as the length of the interval decreases. This suggests that the rock is falling at a speed of 32 feet per second at the precise moment of t equaling 1 second. Let's confirm this algebraically. All right, here's how we're going to confirm it algebraically. All right, remember f of t, let me get me a different color here. F of t equals 16t squared. All right. F of t plus h, which is the new point that is just slid over by an infinitesimally small amount, f of t plus h is going to be substituting in t plus h in the place of t. So 16 times t plus h squared. Now I'm going to expand this, okay? I'm going to do t plus h squared. I'm going to do t plus h times itself. When I do that, you may want to pause it and do it yourself. T plus h times t plus h gives me t squared plus th plus th plus h squared. So it's going to be t squared 16 times t squared plus 2th plus h squared. All right, now I'm going to distribute that 16t squared plus 32th plus h squared. All right, doesn't seem to be anything magical yet, but let's just keep going. All right, now I'm going to do what we said we were setting out to do. F of t plus h minus f of t over h. Again, this is the slope. This is just y2 minus y1 over x2 minus x1. That's all this is. Just written with a different fancy notation. But it's going to accomplish something good. So now this is f of t plus h. And this is f of t. So let's substitute those expressions in there. All right, that's going to be 16t squared plus 32th plus h squared minus, I know it's kind of, my t's and my pluses kind of are confusing because pluses look like t's. Anyway, minus 16t squared over h. Now, do you see something that can simplify on the top? 16t squared and negative 16t squared cancel each other out. So we get 32th plus h squared over h. Do you see anything else that can simplify? Every term has an h in it. So here's how I'm going to simplify. I'm going to factor out an h on top. Gives me 32t plus h. Gosh, I know that's just not easy to read, that handwriting. All over h. And now what happens? The h's cancel. So what does that leave me with? That leaves me with 32t plus h. Okay? But what did we say about h? H is becoming nothing. It's approaching nothing. How close is it to nothing? It is as close as you can imagine, and then more. It's so close you can't stand it. It's so close. So that means that this is 0. This goes to nothing, which means we're left with 32t. 32t gives me the average rate of change, in this case the average speed at any time t. So I can now know the average speed of this function, of this curve. I can know the average rate of, not the average, I can know the instantaneous. That's what I meant to say. I don't know if I said that before, but that's what I meant to say. Yeah, I need to change that. That's not the average speed. The magic here is that this is not an average anymore. This is the instantaneous. Instantaneous rate of change, in this case, speed. This is the instantaneous speed at any time we want to find it. And notice, it is not a constant. It is an expression that changes its value as t changes, which is exactly what we should expect, because the instantaneous rate of change is different here than it is here, and then it is here, and it's just continuing to change the more time passes, right? The longer the thing falls, the faster it's going to go. The greater the instantaneous speed is going to be, which this function exactly accomplishes. So to answer the question, I think the question said for us to verify what is the instantaneous speed at the moment that 1 second hits the clock. All we have to do is plug 1 in for t, and we get it, 32, which is exactly what we saw back here. We have now confirmed it totally algebraically, what we were looking at kind of experimentally when we looked at it here. What would it be, by the way, when t is 2? We just plug 2 in for t. When we plug 2 in for t, what would we get? Plug 2 in for t, 32 times 2, what would we get? Exactly what we saw that we would get, 64. And this is, I mean, I don't know about you, but to me, this is witnessing miraculous things. Like we really just did something that should have been impossible. Something that we can't understand why we can do it using the calculus. Because we made h become 0, and we actually got a good answer that is right. And it tells us the exact slope, not of a line, but of a dadgum curve at any point on that curve. Okay. The average speed of a falling object is an example of a more general idea which we will discuss next. Given any function, y equals f of x, we calculate the average rate of change of y with respect to x over the over the interval x1 to x2 by dividing the change in the value of y, delta y, which you could say is f of x2 minus f of x1, by the length of delta x, which is just x2 minus x1. So that takes us to this definition right here. The average rate of change of any function f of x with respect to x over any interval from x1 to x2 is given by this. And these are two ways to say the same thing. This thing and this thing are equivalent ways of saying the same thing. The only thing that's changing here is instead of saying x2, you're saying that this x2 is x1 plus h. So when you make x2 x1 plus h, this is what you get. So x2 is x1 plus h, and then you subtract x1, so that just reduces the bottom to simply h. All right. Geometrically, the rate of change of f is the slope of the line through those 2 points. In geometry, a line joining 2 points of a curve is a secant to the curve. Thus, the average rate of change of f from x1 to x2 is identical with the slope of the secant. Let's consider what happens as the point Q approaches the point P along the curve so that the length of h of the interval over which the change occurs approaches 0. We will see that this procedure leads to defining the slope of a curve at a point. Okay, defining the slope of the curve. We know what is meant by the slope of a straight line, which tells us the rate at which it rises or falls, its rate of change as a linear function. But what is meant by the slope of a curve at a point P on the curve? If there is a tangent line to the curve at P, a line that just touches the curve, like the tangent to a circle, it would be reasonable to identify the slope of the tangent as the slope of the curve at that point P. So we need a precise meaning for the tangent at a point on a curve. For circles, tangency is straightforward. Any line L is tangent to a circle at point P if L passes through P perpendicular to the radius at P. Such a line just touches the circle. But what does it mean to say that a line L is tangent to some other curve C at point P? To define tangency for general curves, we need an approach that takes into account the behavior of the secants through P and nearby points Q as Q moves toward P along the curve. Here's the idea. Start with what we can calculate, namely the slope of the secant, PQ. So that's the line that passes through point P and point Q on a curve. Investigate the limiting value of the secant slope as Q approaches P. So in other words, we're bringing Q closer and closer and closer to P along the curve. We clarify the limit idea in the next section. If the limit exists, take it to be the slope of the curve at P and define the tangent to the curve at P to be the line through P with this slope. So in other words, we have brought Q to P and have made ourselves a tangent. This procedure is what we were doing in the falling rock problem in the previous example. The next example illustrates the geometric idea for the tangent to a curve. You can kind of see this illustrated what's happening here. Here's 2 points P and Q. And as you bring Q closer and closer to P, you can see the secant, the slope of the secant line, is now approaching the slope now of a tangent line to P. So example 3, find the slope of the parabola y equals x squared at the point 2, 4. Write an equation for the tangent to the parabola at this point. Okay, here's what we're going to do. We're going to apply the thing we've been doing, f of x plus h minus f of x over h, to this problem. That will allow us to find the slope of this parabola at a point. So f of x is just what? It's just x squared. Okay, f of x plus h is substituting x plus h in for x, so it's x plus h squared. If I expand that, you might want to do it yourself, but it's just going to be x squared plus 2xh plus h squared. All right, now, so this is going to go here, and this is going to go here. So that gives me x squared plus 2xh plus h squared minus x squared over h. What simplifies? The x squared, the negative x squared cancel out. 2xh plus h squared over h. What else simplifies? We can factor an h out and cancel the h's. Factor an h out on top, leaves me with 2x plus h. And the h's cancel on top and bottom. So that leaves me with 2x plus h. But we want to find this at a single point, which means the h is going to go to nothing. It's going to go to 0, which leaves me with 2x. 2x allows me to find the slope of this parabola at any value of x. Now, what is it asking me to do? Find the slope of the parabola at the point 2, 4. Okay? That means I know the value of x that I want to find the slope at. All right, let me draw this for you a little bit. I've got this parabola. Y equals x squared. I've got 1, 1, I've got 2, I've got 2, 4. Okay. All right. Sorry. Okay. So I'm trying to find the slope of this parabola, of this curve at this point right here. So I'm trying to find the slope of this tangent line right here. So all I've got to do is use what we just found, which is that the slope of the tangent line, slope of tangent line at any value of x is 2x. So what is the value of x here? It's 2. So I just plug in 2 and I get 4. The slope of that tangent line is 4. I've now answered the first part of the question. The second part of the question says, write an equation for the tangent. In other words, I've got to figure out the equation for this tangent line right here. Okay? Whatever that tangent line is, I've got to find the equation of it. All right? What's the equation of a line? Y equals what? Mx plus b. What do I need to know to find the equation of a line? I need to know m and I need to know b. All right, I do know m, don't I? M is 4, but I don't know b. But we're going to be able to find it using the information that we already have. Here's how we do it. I actually can plug something in for the x and y because all I need is a point on that line, and I can use that xy coordinate to plug it in for x and for y, and now the only thing I'll be missing is b. And what's that? That's the point 2, 4. There's your x, there's your y. Plug in 4 for y. Plug in 2 for x. And figure out what b is by doing just a little bit of algebra. 4 equals... I'm sorry, I see now I wrote something wrong right here. M is 4, I accidentally wrote 2 right there. I'm plugging 4 in for y. M is 4. I'm plugging 2 in for x. And I'm solving for b. Okay. So 4 equals 8 plus b. Subtract 8. And negative 4 is b. Now I have the equation of my line. The equation of this tangent line is y equals 4x minus 4. And now I've answered the whole question. All right, we answered that question very well now. Moving on. Instantaneous rates of change and tangent lines. The rates at which the rock in example 2 is falling at the instants t equals 1 and t equals 2 are called instantaneous rates of change. Instantaneous rates and slopes of tangent lines are closely connected. In fact, they are the same thing, as we see in the following examples. All right, figure 2.5 shows how a population P of fruit flies grew in a 50-day experiment. The number of flies was counted, and the counted values were plotted with respect to time, and the points were joined by a curve. So they plotted these points that they figured out, and then they just drew a curve to connect the dots, and this is the curve that modeled that population of fruit flies as it grew over time. Then it tells us to do this. It says find the average growth rate from day 23 to day 45. All right, find the average growth rate from day 23 to day 45. So I'm looking at my curve. I don't have a function in this case. I just have a graph. Like I don't know what the function is of x that will model this curve. But I don't need it if I've got the graph. I can just kind of go along the graph to get my answer. So here is the point where the day, on basically day 23 is about that point right there. So they kind of estimate that to be the point 23, 150. Here is the point for day 45, and they estimate that to be pretty much the point 45, 340. And if we want to know the average rate of change, right, the average growth rate of the fruit fly population. This time it's not average speed, it's the average growth rate of the population of fruit flies between those 2 days. In other words, over that interval of time, all we need is the slope of the secant line. Remember, average rate of change, average rate of change is the slope of the secant line. Okay, so we find that just by doing the good old slope formula from the good old days. We do y2 minus y1 over x2 minus x1. So 340 minus 150 over 45 minus 23. And I'm sure they did that down here on the on this example. Actually, they did it right here. It's right here. 190 over 22, which is about 8.6 flies per day. So this averaged a growth of around 8.6 flies per day. Now you can see, according to the curve, it's not that same rate every day. It's just that that's the average rate. So like at first it was growing faster than that. Then it kind of slowed down, and toward the end it was going even slower than that. But over the long haul, The average was about 8.6 flies per day. Okay. My computer's not working too good for some reason. All right. The average rate of change from day 23 to day 45, calculated as example 4, does not tell us how fast the population was changing on day 23 itself. For that, we need to examine time intervals closer to the day in question. How fast will the number of flies in the population in example 4 growing on day 23? So not over a interval of time from this day to another day, but just on that particular day itself, how fast was it growing? So here's how we do that. All right, because we don't have an algebraic function defined for us, we can't do the technique we did before where we're doing the f of x plus h minus f of x over h and simplifying things and finding the exact value. What we're going to do, because all we have is a graph, is we're just going to try to make ourselves a line that is tangent, that kind of goes along exactly what the slope of that curve is. That's tangent to that curve. And then figure out what any 2 points along that line and find the slope of that bad boy. So the 2 points that they chose to use along this line are this point and this point. So they just found the slope of that tangent line by kind of guesstimating it and using the 2 points along that guesstimated line. So they said 350 minus 0 over 14, sorry, over 35 minus 14, which is 350 over 21. And they came up with approximately 16.7 flies per day. So on day 23 itself, it was growing very fast. It was growing at 16.7 flies per day. And it continued on pretty close to that rate for a little bit, but then it slowed down over the next bit of time. All right, the instantaneous rates in example 2 were found to be the values of the average speeds or average rates of change as the time interval of h approached 0. That is, the instantaneous rate is the value the average rate approaches as the length h of the interval over which the change occurs approaches 0. The average rate of change corresponds to the slope of the secant line. The instantaneous rate of change corresponds to the slope of the tangent line. Okay, that is the crux of this little unit here. The kind of the summary climax is that statement. That statement right there. The average rate of change is what? The slope of the secant line. The instantaneous rate of change is what? The slope of the tangent line. All right. And calculus allows us to find the slope of the tangent line that would be impossible to find otherwise. It tells us we investigate this connection thoroughly in the next chapter, in other words, in chapter 3. But to do so, we need the concept of a limit. And we're going to develop the concept of a limit much more precisely throughout chapter 2. So that's the end of section 2.1. Good luck on that homework assignment. See you next time.